ହଉ 5-10 ମିନିଟ୍ ଅପେକ୍ଷା କରୁଛି, ଆସନ୍ତୁ କି ଆସନ୍ତୁ ଦେଖିବୁ।
ହଁ ସାର୍ ଠିକ୍ ଅଛି, ମୁଁ ଆଉ ଥରେ କହିଦଉଛି ସମସ୍ତଙ୍କୁ ନହେଲେ ଗ୍ରୁପରେ।
ଓକେ। Okay. Good evening to all of you.
Good evening, sir. Namaste.
Only 5. So we shall start. This is your organic chemistry class. So we have been taught inorganic chemistry by Subhasima Das. Yes or no?
Yes, sir.
So please don't be late for the next class because we have the syllabus is very vast and to finish the syllabus. So you should be in time so that we can start. Okay. Anyway, so generally, how many of you are joining? So only the 7 or more than this? Hello?
Sir,
You are only 7 or still others are there. They are not joining. Shall we wait or we'll start?
स्टार्ट करदबा सर काहे के जॉइन करना
How? जे join କରୁଛି କରୁ ଆପଣ will start.
आज्ञा
I'm sharing the screen. Is it visible?
Yes, sir.
yes, sir.
Okay. So your organic chemistry part 2, which mainly deals with the heterocycle compounds. So far as your syllabus is concerned, containing one ring and large member heterocyclic, more than one ring. Then basic concept of organic synthesis and some more approaches on organic synthesis. So 4 blocks are there. So I don't know how much we'll cover. Still, we'll start from the beginning. That is introduction to heterocyclic compounds. Can you tell what is heterocyclic compounds? What are heterocyclic compounds? Anybody? These are the cyclic compounds containing heteroatom other than carbon and hydrogen. As you know, hydrogen is monovalent, so it never be inside the ring. Carbon will be there, forming cyclic compounds, or as you know, out of in organic chemistry, the organic compounds or hydrocarbons, they are mainly divided into 2 categories, cyclic and acyclic. In acyclic, you have aliphatic or alkane, alkene, and alkyne. In cyclic, you have alicyclic, heterocyclic, and aromatic. Alicyclic compounds, they contain only carbon in the ring. They are ring-like structure containing only carbon. Whereas heterocyclic compounds, they contain heteroatom. So heteroatom means the heteroatom may be nitrogen, oxygen, sulfur, to some extent there may be barium, okay, selenium, phosphorus, boron, silicon. These are the heteroatoms which are generally present in heterocyclic compounds. So first we will see the nomenclature. So far as the syllabus is concerned, we have to move with the nomenclature of heterocyclic compounds. So nomenclature, it is based on the 3-member, 4-member, and also 5-member up to 6-member compounds. And the nomenclature, it is based on four types of or four systems. First one, the trivial or common system for nomenclature. Then Hutch-Widman nomenclature, fusion nomenclature, and replacement nomenclature. So all these four types or four systems of nomenclature is recommended by IPAC. So as in case of simple organic compounds other than heterocyclic, we have a common name or trivial name, and we have the IPAC system for nomenclature. These two types of nomenclature are there. But here we have four types, and all four types of nomenclature are recommended by IPAC. So anyone we can take to name the heterocyclic compounds. So what are the learning outcomes? So we can nomenclate various systems for the heterocyclic compounds. What are the state of rules of different systems with their appropriate example? Then how can we write the name? So then we'll move to the second unit. Okay, that is the spectral characteristics of heterocyclic compounds. Then aromatic nature of aromatic heterocyclic compounds and their characteristics, and reactivity of heterocyclic compounds. So far as the nomenclature is concerned, as I told, we have the heteroatoms like oxygen, nitrogen, sulfur, selenium, silicon, and tin also there. And number of heteroatoms also increases. It may be 1, 2, or 3. And ring, number of carbon atoms in the ring, that is also, it is starts from 3. 3-membered ring, including heteroatom, 4-membered ring, and if it is 5-membered ring, when it will be 5-membered ring, so maybe 2 heteroatoms may be present. But in case of 3-membered ring, there may not be 2 heteroatoms because of, as you know, Bayer's strength theory. Only carbon and very few compounds which contain heteroatom in a 3-membered ring, maybe oxygen and sulfur only present if you consider the heterocyclic compound containing 3-membered ring. So we'll discuss the different types of nomenclature, the trivial or common name. First we'll discuss the common name or trivial name. So this name, it is also written by IPAC, as we have seen from this slide or the screen. Some examples of different structural types here given. If they are saturated compound containing only one heteroatom, that is nitrogen, and 3-membered ring, so you can say it is aziridine. And if it is oxygen, then ethylene oxide, or also known as oxyren. If sulfur is there, then thio, you know, thio for sulfur, so it is thyrene or thyrene. And if it is a 4-membered ring containing oxygen, then it is oxytane. It is oxyren or ethylene oxide. This is oxytane. And if nitrogen is there in a 4-membered ring, then it is azitidine. It is aziridine, 3-member. For 4-member, it is azitidine. And thio for sulfur. If 4-member sulfur ring is present, then it is thietane. I'll give if the number, depending upon the number of members present in the ring, then there are different prefix we have to use. So if it is a saturated ring, first we'll move to that one. That is given by Hans and Widman system. So we'll discuss that on later on. First the common name. So we have to just remember, but the formula or the rule that is starts from the second type of nomenclature, that is the Widman system. Widman system. So if it is 5-member containing nitrogen, it is pyrrolidine. This is tetrahydrofuran. Oxygen, if is there, if nitrogen, and 6-member, then it's piperidine. If it is unsaturated or aromatic, then it is known as pyridine, as you know. If it is saturated, then piperidine. And here, if 2 oxygen, so oxa is the prefix, so dioxane. and it is 1,2 dioxane. This is 1,4 dioxane. If they are in, depending upon the position, from one oxygen we have to start. We'll move to the second oxygen. As you know, in IPAC nomenclature, the second heteroatom should be given the minimum locant. We'll start from the one heteroatom, we'll move to the second, which will have the minimum locant. So it is 1,2, not 1,6. So 1,2 dioxane, this is 1,4 dioxane. If they are aromatic, that means unsaturation will be there. So 5-membered rings containing unsaturation and nitrogen as the heteroatom, then it is pyrrole. If oxygen, furan, if sulfur, it is thiophene. These three you know in your higher secondary or +2 when you are nomenclating the organic compounds. If 2 nitrogen at 1,2 position, then it is pyrazole. If at 1,3 position, 2 nitrogen, imidazole. 1 nitrogen and 1 oxygen, oxazole. In 1,3 position, if it is 1,2, then isoxazole. Okay, have to remember this thing. 6-membered ring, then pyran containing 2 double bond, again aromatic. This is because this lone pair will take part in the conjugation system. So pyran, pyridine, pyridazine, 1,2 dinitro system, 1,3 dinitro is pyrimidine, and 1,4 is pyrazine. Now moving to the condensed or fused heterocyclic compounds. Indole, 1 6-membered fused with a 5-membered ring containing 2 nitrogen at 1,3 position. Then it is indole. 1 oxygen, that is benzofuran. If 5-membered ring, only 5-membered, then it is furan. So benzene is attached or fused, so benzofuran. At first position, if nitrogen, quinoline. At second position, then it is isoquinoline. Similarly, carbazole, purine containing 4 nitrogen, and if it is 5 member and 1 6-member, if both have 6-member containing 4 nitrogen, then it is petridine. So these are the prefix which are used generally for heteroatoms. For oxygen we have to use oxa, for sulfur thia or thio generally, but here it is thia. All are ending with a. Oxa, not oxo. There we are using thio, it is thia. Selenium, selena. Nitrogen, for nitrogen you are using azo, as you know, but here in this case it will be aza. Phospho, then it is phospha for phosphorus. Silicon, sila, and boron is bora. And the priority, while two more than one heteroatom will there, so priority will be given. Highest priority is oxygen. From left to right, it will decrease. Okay, so the priority, increasing priority order of atom is from right to left. That means it will decrease from left to right. So oxygen will be given the first priority, then sulfur, then selenium, then nitrogen, then phosphorus, then silicon, and at last it will be boron. Okay, so the trivial name, similarly, this is already we have known, furan and ethylene oxide, or in trivial also it is known as ethylene oxide will be oxacyclopropane, furan will be oxacyclo 1, 2, 3, 4. So 2,4 diene. Oxacyclopenta 2,4 diene. That is the IPAC name, and based on IPAC, but it is the common name or trivial name which is recommended by IPAC. So furan is the trivial name, but if you convert it to IPAC system, then it is oxacyclopenta 2,4-diene. Now we'll move the next system of nomenclature, that is Hans-Widman system. So the suffix for different heterocyclic compounds, depending upon the ring size, if it is saturated, will give all are with ane. It will end with ane. So for a 3-membered ring, we have ir. So iren. If unsaturated, then it is irin, ene. For 4-member, it is eten, ane. This is ane, iren. This is eten, etane. Then olen for 5 member. For 6 member, inen. 7, epen. For 8, we are using octa there. So it is oken, ocane, oc. So oken. For 9, onen, on. There you are using non. It is on, ane, onen. And for 10, eken, ECANE. So IR, ET, OL, IN, EP, OC, ON, and EC. So like this, you have to remember 3 member: ear, et, ol, in, ep, ok, on, ek. And if it is unsaturated, the ANE will be ENE. Okay, but these three you just see. For 4 member, 5 member, and 6 member, the NE is not there. So only ETE, OLE, INE. Why this is? It is in the next rule. We'll just check that one. Okay, so this you can see here. Before we actually understand the example of naming the compound, the following details or exceptions are also to be kept in mind. The suffix "-ene" is used for nitrogen containing 3-membered unsaturated heterocyclic compound. First table you can see there. IRENE. Okay, for 3-membered unsaturated, we have written here IRENE. But when nitrogen will be there, so it will be IRINE. This is the exception. Okay, then again for 3, 4, and 5 member, 3, 4, and 5 member saturated nitrogen containing heterocyclic compounds. Nitrogen containing heterocyclic compounds, 3, 4, and 5 member. That is exception. For other case, we are using eren. But if nitrogen will be there for 3-member ring, we have to write iridine. They are eten in case of 4-member ring. Just see this one. For 4-member, it is eten, but if nitrogen will be there, then it will be etidine. Similarly, it is olen for 5-member. For nitrogen, if हेलो
sir.
अरे मु डिस्कनेक्ट हो जाइए कि केतेबेଳु हेलाणी
2 minutes ki 3 minutes ago, sir.
you write down my phone number. If there will be some this thing, then you can just contact me, so that because I am sharing the screen na, so I could just I asked the question, I could not get the answer, that's why I come to the screen and say I've been signed up. Anyway, so it is, write down my phone number 8249 666 843. Is it clear?
8249 666 843.
Yeah. Okay. Now it is share or not? No. Okay. From where I left? These exceptions I am telling. Yes or no?
Exception, sir.
Okay. Okay, just go through. Then tell me
Cheap
the.
ହେଇଥିଲା 4.2 rest ଥିଲା.
Okay, okay. ସେ ଆସିବ ସେ nomenclature କଲା ବେଳକୁ ଆସିବ. ସେ
Sir.
So ajo, this aja you cannot use. That is the main point here. Azin should not be used because ajo is used for n single bond n, double bond n. This is the azo group, diazo group. So we cannot use azin if there will be a group like this. So we can use pyridine. For pyridine, azine should not be used there. Similarly, for pyran, axine cannot be used because it is a trivial name for quinoline 8-OL. So this example I gave you, this is oxygen or ethylene oxide. Common name is ethylene oxide. So in IPAC system or whatever we are using now, the Hertz-Weidmann system, ethylene oxide, it is oxygen is the heteroatom. So for oxygen, the prefix is oxa, and for three-membered ring, it is eren. You can go to the table 1.2. You can see there. So it is oxyren. So when we are using this compounding this, adding this one, this A we have to omit. So oxa, from oxa A will be removed. So IRANE, so oxyren. Similarly, for nitrogen, we have to use aza. You can refer the table 1.1. For nitrogen, the prefix is aza, and for three-membered ring, if it is nitrogen, I have given the exception there. For nitrogen containing three-membered ring, irene is used. You can go to the table, you can see for three-membered ring it is irene. But if nitrogen is there, then it is irene, I-R-E, sorry, then it is iridine, I-R-I DINE. So azaridine, A will be removed. So it is aziridine. So in same way, can you nomenclate this system? How do you nomenclate? Name the following system using Hans-Weidmann system. Sulfur is there. So for sulfur, yes. What is the prefix?
Thiatin.
Thia, eten. So A will be removed. It is thiaten.
Thiatin.
Please mute. Thiaten. TH. Please mute. It is thiaten. So thiaten. And here oxygen is there. So it is oxa and five-membered ring. So five-membered it is olen. So A will be removed. Oxolane. OXOLANE. and here it is a sulfur, and number of atoms, 8 membered ring. So 8 member we have ocane, OCANE, sulfur is thia again. So thiocane, THIOCANE. Okay. So this one, when the same heteroatom is present 2 or 3 times, then we have to use di-tri these things, and we have to number the atoms so that we'll start from one heteroatom, so that the other heteroatoms they will get the lowest set of locants. So this one, so 2 oxygens are there, and it is a 5-membered ring. So for 5-member, we have Olen, OLA, Any, and oxo is there. 2 oxygen, oxo means dioxo, and then we have to see the position. So 1,3 dioxolone. Okay, 1,3 dioxolone, and here again 5-membered ring. So Olen should be there, and it is a unsaturated, so it will be OLE. Last will be OLE. 3 nitrogen triazo OLE. So triazole, and then what are the position? One. If we move in the clockwise, then 1, 2, 3, 4, 5. So 1, 3, 5. But to move in this case, so 1, 2, 3, 4, 5. So 1, 2, 4. So it will be 1, 2, 4 triazole. Same as in organic, we are nomenclating or giving the locant to the atoms. This one, 2 nitrogens are there, so it is pyrimidine, pyrimidine. So that is approved by IPAC. So 1 and 3 position you have nitrogen. So in 1, 3 you have 2-azo, diazo, and if it is 6-membered ring, the suffix will be ine. So diazine, 1, 3 diazine. Clear? So what will be this one? What will be the
One,
name of
three.
this one? 1, 2, 3, 4, 5. 1, 3, 5. Triazine. This is diazine, same thing, unsaturated. So IN will be there, and azo, nitrogen for azo, so azine. 3 nitrogen, triazine, and position 1, 3, 5. 1, 3, 5 triazine. When the heteroatoms are different, then we have to give the priority. Oxygen as the first priority. If present, then sulfur, then nitrogen, phosphorus, arsenic, silicon, at last it will be boron. So the name is a combination of prefixes in order of the above priority order. So let us nomenclate this one. Sulfur and nitrogen is there. So between sulfur and nitrogen, sulfur is the first priority. So it should be given the lowest locant, that is 1. Then we'll move towards nitrogen in such a way that it will give the next locant. So 1, 2, 3. If you move clockwise, then it is 1, 2, 3, 4. So anti-clockwise you move. So 1, 3. So 1, 3. Then for sulfur, we have to nomenclate first thia. For azo, it is aza. And as it is a 5-membered ring, it will be OLE. Suffix will be OLE. So thia, aza, OLE, and this one A we have to remove. So thiazole, thai, aza, OLE. So this, when vowels will be there, one vowel we have to remove. Generally A we have to remove. So thiazole. If 2A, so we have to remove 1 and we will keep 1. So thia, aza, from aza A will be removed, ol. So thiazole, and position 1, 3. 1, 3 thiazole. Okay. Similarly, this is thietane, this is pyridine. This is not right. Okay. So when different will be there, this is already, we know this one. 1,3-oxazole, oxygen, then azo. Similarly here sulfur and nitrogen is there. Sulfur is having first priority. In between I have to check. Why I am losing my connection? Is it okay now? Hello?
ओके सर ओके
କ'ଣ ହଉଛି କାହିଁ ନେଟୱାର୍କ ପଳେଇ ଯାଉଛି ମଝିରେ ମଝିରେ, ମୁଁ ବୁଝିପାରୁନି କିଛି।
हाँ सर कटि आसुन आपण ଟିକେ ଥରେ स्क्रीन शेयरिंग आसनी आपण खाली माने आसे
ନାଇଁ
स्क्रीन शेयरिंग आसे
ସେୟାରିଂ କରୁଛି।
आगे
We'll move to the fusion nomenclature. That means two rings, they are fused or joined together by a common bond. Two or more cyclic units joined by a common bond. So in these compounds, the heterocyclic ring is chosen as the base ring. So when two rings are there, one contains the heterocyclic heteroatom, then that will be the base ring. So basing upon that, we have to give the nomenclature. So basic ring, you can see the 5-membered ring, aromatic. So it is furan to furan. Benzene ring is attached or fused. So it is benzofuran. Okay. Similarly, what will be here? Oxygen and sulfur. These are two heterocyclic rings. They are fused together. Both are 5-membered. And only in one case you have oxygen and one case you have sulfur. So oxygen is having first priority than sulfur. So this ring will be the base ring. So if this is base ring, then nomenclature should be furan. Base ring is furan. And if sulfur is there, so for sulfur, 5-membered ring. So what is the name? Tell. 5-membered containing sulfur. We have discussed now. 5-membered ring containing sulfur. Thialone. Yes or no? So it will
Yes,
be
sir. Thiol.
thialofuran. Like benzene, we have removed Ne, we have written benzofuran, so it will be thialofuran. Here nitrogen and oxygen is there, so nitrogen will be given the priority. So pyrrole, base ring is pyrrole, and it is furan. So furan, nitrogen. Yes, if nitrogen will be there, so nitrogen will be the base ring. In case of the second compound containing nitrogen, if nitrogen will be there, then nitrogen must be in the base ring. So priority will be given to nitrogen. Okay. Third rule, in case of rings unequal size containing the same heteroatom, then the larger size ring will be the base ring. So larger has 6 members, so it is pyran. This is furan, so furanopyral, like pyran, it will be the name. If they will have same size, then in same size you may have different heteroatom, you may have the same heteroatom. So when number of heteroatoms is different, the base ring is that ring which contain more number of heteroatoms. Here it contains two heteroatom, oxygen and nitrogen, so base ring will be the oxazole one. If equal number of heteroatoms are present, and when these atoms are same, the ring having the lowest number given to the heteroatom will be the base ring. So we'll start from here: 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2. So lowest locant is 1, 2. If you start from here, then 1, 1, 4. So it is not the lowest locant. So lowest locant is 1, 2. So it is pyridazine is the base ring. If they are different, then the greater variety of heteroatom will form the base ring. Okay, so here oxazole is the base ring. Then ring with priority order given earlier for heteroatom is the base ring. Here some highlight is different. So here priority oxygen and oxygen is having higher priority than nitrogen. So this ring is the base ring. That is oxazole is the base ring. The shading is wrongly there done here. So oxazole is the base ring. Like this we have to move. Then bicyclic or polycyclic systems. So in that case, so bicyclic or polycyclic system can also be chosen as the base ring, and their common trivial name can be used for this purpose. If you see this one, then it is quinoline. So quinoline is the base ring, and we have to add this one to quinoline. The sides of the base ring are labeled as A, B, C as shown. A for 1,2 bond, 1,2A, B for 1,3 bond, C for 3,4 bond. 1,2 is A, 2,3 is B, 3,4 is C, then 4,5 is D, and 5,6 is E, like this. And again 6,1 is F. So the atoms of other rings are numbered as 1, 2, 3 according to the lowest possible. This is for base ring. The attached ring is indicated as a prefix, and its ending E is changed to O. For example, for benzene attachment, we are using generally benzo, that already we have discussed. Similarly, for pyrazole, we have to use the pyrazole ring. E will be replaced by O. So pyrazolo is added. Okay, pyridine, pyrido, for pyridine, pyrido, for quinoline, quino, for furan, furo, for thiophene, thiino. Okay, as in this case, you can see the total, this one A, and where is the fuse? At B, there is fusion, so it is benzo B furan. benzofuran or benzo B furan. If here, then benzo C furan. Understood or not? If the system this will be here, oxygen will be here, then it is benzo C furan. It is benzo B furan. Similarly, another compound shown below, that is a benzene ring attached to thiophene. So what will name this one? At C position, the benzo C thiophene you can see here. It is C side, so name is benzo C thiophene. Why this problem is persisting, I don't know. Everything is okay. Why I'm losing my connection? Then again it's coming back automatically. Sorry. Is it okay? Hello?
Okay, sir.
Yes, sir.
Okay, sir.
କଣ ହଉଛି କାହିଁକି ପଳେଇ ଯାଉଛି ମୁଁ ଜାଣିପାରୁନି. Okay, so these things you do the exercise will not take much more time. So again, where used to comma and where hyphen, these things also you know the same thing what we are using in common nomenclature of organic compounds. If two digits are there, we have to separate by comma, and number and syllable they are separated by hyphen. So like here, pyrazino 23C pyridazine. Okay, this is pyridazine and this is pyrazine. 1,4 position is pyrazine, 1,2 position is pyridazine. Diazo, like diazo. Okay, from you will start from pyridine, then diazo are there, so diazo in, so pyridazine. This is pyrazine, 1,4 position is pyrazine. When they are fused together, so this 1,2 position, there is the heteroatom, so this will be the base ring. So base ring is pyridazine. Okay, and 2 pyridazine at position C, that means this bond it is fused. So it is fused at 2,3. Okay, so 2,3C. So pyrazino, from pyrazine we have pyrazino, and 2,3 position, the C of this one is attached, so 2,3 and C they are fused together, so 2,3C pyridazine. So you can see here clearly, here the base ring is pyridazine. If the C side of pyridazine is fused with 2,3 side of pyrazine, we get the above structure. So it is pyrazino 2,3C pyridazine. Similarly, this one you can see the where it is attached to the D side, means here, this position. So D here it is attached. So same thing, pyrazino, and it is 2,3 of pyridazine. Pyrazine it is attached. So 2,3, but from pyridazine, it is the D side. So pyrazino 2,3-D pyridazine. Okay. Some other examples are also there. You can see that one. So here we end the first. Okay, another is the replacement nomenclature. So that we have to study. Small one. This system is based on the name of the related carbocyclic compound to which the appropriate prefix of the heteroatom like aza, oxa, thia, etc. prefixed. You can see here, if oxygen will be not there, this is cyclopropane. So replacement means one carbon is replaced by oxygen. So we can see for oxygen we use oxa cyclopropane. That oxygen is also known as this easy oxacyclopropane. And for nitrogen, we know aza will be used and cyclobutane. Azacyclobutane. Similarly for sulfur, thia cyclopentane. Okay. For 6 member, it should be cyclohexane, and 2 double bonds are there at 2 position and 5 positions, so 2,5-diene, cyclohexadiene, and oxygen is there, so oxa cyclohexa 2,5-diene. Similarly, sulfur and nitrogen are there. Sulfur is the first priority, nitrogen at 4th position, sulfur at 1 position, so 1 thia, 4 aza, cyclohexa 2,5-diene. It's a simple one. Similarly, here 2 position methyl is there, so 2 methyl aza cyclohexane. Okay. If in case all the 3 double bonds are similar to benzene, if all the 3 double, here 2 double bonds are there, if you move for 3 double bond, then if 3 double bonds are similar to benzene, then we will use the suffix benzene. Okay, because the CH is removed by the heteroatom. So it will be aza benzene, this will be phosphor benzene, like this. Okay. Similarly, this is anthracene. If we remove, then at 2 position nitrogen is there and 5 position nitrogen, because when we are using fused system, you just see we are giving the number as 1, 2, 3, 4, then 5, 6, 7, 8, 9, 10. But here as the heteroatoms are there, so the middle ring we have to number the first in the cyclic order. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at 5 and 2 position you have 2 nitrogen, so 2,5 diaza anthracene. Okay. So this is all about the nomenclature. Then the characteristics, special characteristics of heterocyclone compounds. We study here the UV visible spectroscopy or UV visible characterization, IR, NMR, all these things, and you should know the basic things regarding the IR, NMR. Yes or no? Did you know or not? If you are not giving any answer, then I have to see whether I have lost my connection or not. No, I am not disconnected. You know the basic things or not regarding UV, IR, and NMR? Anybody?
ହଁ ସାର୍ ଟିକେ ଟିକେ
What?
ମନେ ଅଛି
হ্যাঁ হ্যাঁ ଟିକେ ଟିକେ ମନେ ଅଛି।
ଟିକେ ଟିକେ ହଁ ସାର୍ ଟିକେ ଟିକେ
ଠିକ ଅଛି ଟିକେ ଟିକେ ମନେ ଅଛି ତାହେଲେ ଚଳିବ ଆଉ ଦେଖିବା କଣ କେତେ ମନେ ଅଛି। Because these heterocycle compounds, in case of if you see simple aromatic or hydrocarbon, if it will not contain heteroatom, only carbon and hydrogen, the bond strength or bond is less polarized than if there will be a heteroatom. So all the organic compounds, depending upon the bond strength, they are sensitive to different types of radiation. And if you know the complete electromagnetic spectra, then UV visible radiation is having higher energy than infrared. And NMR is a little bit different that we'll discuss, or it is not, it is coming under infrared, sorry, electromagnetic spectroscopy, but here it is resonance, nuclear magnetic resonance. What is the full form of NMR? But UV and IR, they're under electromagnetic radiation. So between UV and IR, UV requires higher energy because it is in lower wavelength. Ultraviolet wavelength is lower than infrared, and infrared, the energy of infrared is much more lesser than UV. So far as the spectroscopy is concerned, when any substance, organic compound is irradiated by UV or visible light, there will be electronic transition. So that's why UV visible spectroscopy is also known as electronic spectra, because electron will transfer from one molecular orbital to other molecular orbital. As you know, there is bonding and anti-bonding molecular orbital. So electronic transition will occur from bonding to anti-bonding molecular orbital. So sigma, pi, if they are the bonding molecular orbital, their respective anti-bonding molecular orbitals are sigma star and pi star. Moreover, if the compound contains any lone pair of electron, and that must be present in a non-bonding molecular orbital, you can represent it as n. So there will be n pi star transition. So there are minimum 4 types of transitions are there: sigma sigma star, pi pi star, n sigma star, and n pi star. And if you will recall that why sigma pi star and pi sigma star, this type of transition is symmetry forbidden due to symmetry of molecular orbital. So just I repeat again, sigma pi star and pi sigma star, these transitions are energy symmetry forbidden. So 4 types of transitions are there: either sigma to sigma star, or pi to pi star, and n to pi star. And this in heterocyclic compound, as the heteroatom, they contain a lone pair of electron. Each heteroatom, you can see oxygen, 2 lone pairs are there; nitrogen, 1 lone pair is there; sulfur, again 2 lone pairs. Okay, so basically all the heterocyclic compounds, they have a lone pair of electrons. So more prominent that n pi star transition will be there. Okay, and due to this n pi star transition, and if you can recall the energy level diagram, sigma sigma star transition requires much more energy than pi pi star, and n pi star transition requires the least amount of energy. So due to that, if least amount of energy required between UV and visible, ultraviolet radiation is having higher energy than visible. So if the atoms are there containing lone pair, so n pi star transition that occurs between, you can see here the wavelength 270 to 340 nanometer, which is in the far UV region or it is towards the visible region. That's why all heterocyclic compounds looks colored. So different compounds and their UV spectra are written here. The transition, you can see the lambda max is at 251 for pyridine containing only one heteroatom nitrogen. And here pyridazine, two are there. So what will happen? The wavelength, the lambda max value for pi star transition, it decreases. But you can see the n pi star transition, it increases. Because due to this presence of lone pairs are loosely bound now. Here only one lone pair, here two lone pairs are there, two nitrogen atom there. So this is 340, 270, it increases to 340. 340 means it is just coming in the visible region. Visible region is 360 to 720 nanometer, 360. So it is around 340 means just towards the visible. Okay, and this is molar extinction coefficient log E, that you know, that is the intensity of bands. If you go for this UV visible spectroscopy is governed by two laws, Beer's law and Lambert's law. Okay, so molar extinction coefficient, that is the value which give you the intensity, lambda max. The to know the UV spectroscopy curve, you have to plot the curve intensity versus wavelength. Where intensity will be more, okay, that band it will be more intense, means it looks, the color will be, or the band peak will be very depth. So anyway, so you can see or compare. If it is 1-2 position, the n pi star transition at 340. If it is 1-3, as in case of pyrimidine, it again decreases to 298. If it is 1-4, again due to the conjugation, then lambda max value of n pi star transition increases. And for benzene, this is the pi star transition. Okay, there is no n pi star transition. It's only pi star transition which occurs. Why this is coming? At 254. So protonation of nitrogen atom of the ring, if there will be protonation, if here H plus will be added, so what will happen? This lone pair that is not available for n pi star transition. So that's why it will eliminate the n pi star band from the spectrum, but it increases the intensity of pi star band without changing its position. Am I clear? If this molecule will be protonated, that means when it's, because these are nitrogen containing compounds, they are basic. So if you add acid, then it will be protonated. So N minus H plus it will be added here. NH plus will be there. So when it will be protonated, the lone pair of nitrogen makes bond with H plus. So they are no longer available for N pi star transition. So in such case, the N pi star band is eliminated from the spectrum, but it increases the intensity of pi star band without changing its position. Bicyclic systems such as isoquinoline exhibits more complex structure in their UV spectra. Okay, now you can see here UV spectra of monocyclic 5-member heterocyclic compounds. You can see here there is no, because NH, the pyrrole, the lone pair which was over nitrogen, so now it will be in the aromatic system that will take part in the conjugation, so it is no longer available for n pi star transition in such case. So pi star transition that occurs at 210 and where the maximum epsilon max or molar extension coefficient increases 5100. It increases to 10,000. So it will increase. So the n pi star transition is not observed in them because the larger here the S character and the smaller size of the ring. Then you spectra of bicyclic compounds with 5-membered heterocyclic rings. Indole, benzothiophene, benzofuran, and purine. In all the cases, 5-membered heterocyclic. You can see the lambda max in nanometer. You have 3 positions here. 3 lambda max value will get 3 peaks one at 288, one at 261, one at 213. In case of this system, the lambda max value shift towards the higher wavelength. For example, if you take the benzothiophene, so which is absorbed at 288, 257, 227. So as compared to thiophene, in case of thiophene, it is observed at 235. So 235 is shifted to 288. Then we'll move to the infrared spectroscopy. So what happens in infrared spectra? It is basically, this is the vibrational spectra. So why vibration? Because here there will not be any electronic transition. The molecule or the constituent atoms of the molecule, they will vibrate in their mean position, because infrared, the energy of infrared radiation is less in comparison to UV. So UV radiation, if you give, there will be electronic transition, but infrared radiation is not sufficient to transit the electron. But when the molecule will absorb infrared energy, its vibrational frequency or its vibrational energy level will change. As you know, in each electronic level, it contains some vibrational energy level and also rotational energy level. So this is when vibrational energy level will change by absorption of infrared radiation, obviously the rotational energy level will also change. So this is known as rotational vibrational spectroscopy or infrared spectroscopy. So in this case, this is Hooke's law. From Hooke's law, we have derived this one, the vibrational frequency, which is 1 by 2 pi c root over of k by mu. So where k is the force constant, which is related to the bond strength, and mu is the reduced mass, that is m1 m2 divided by m1 plus m2, and c is the velocity of light. So from Hooke's law, putting this value of force constant or bond strength, we can find out the vibrational frequency. The stronger the bond between two atoms, more will be its vibrational frequency. If this will be more, K value is more, then frequency is also more. So the bond strength in turn are related to the bond length. Hence, if the vibrational frequency is more strong character is indicated. In other words, we can say that the decrease in the vibrational frequency indicates reduction of bond order. So this is the vibrational spectra, IR spectra for benzene, pyridine, and pyrimidine. So what happens? What are the characteristics peaks? What that we will get in infrared spectroscopy, IR spectroscopy. If you compare benzene, it is having one 6-membered ring containing only carbon and hydrogen. So we will have one carbon-carbon bond and carbon-hydrogen bond. Just imagine the benzene C6H6, to each carbon, 6 hydrogens are attached. And carbon carbon, you have the double bond and single bond. You can say this is due to resonance, you will get a pi electron cloud, and all carbons are strongly attached, and the carbon hydrogen bond is loose, or the energy of carbon hydrogen single bond length is more, so it requires lesser energy for its vibration or stretching or bending. So three types of vibration will be there. Sorry, two types of vibration will be there. Either it is stretching or bending vibration. Stretching means two atoms when they will just move far away from each other and come closer to each other. That vibration. Along the internuclear axis, they will vibrate with relatively from one another. But bending vibration, they will bend through the plane. If your internuclear axis is the plane, then they will bend maybe over the plane or below the plane. So So stretching vibration and bending vibration will be there. So the aromatic CH saturated stretching frequency appears above 3000 centimeter inverse, and bending vibration is observed between 1300 to 1000 centimeter inverse. In plane bending, if it is out of plane bending, then it is between 700 to 1000 centimeter inverse. In plane bending and out of plane bending, two things are there. That how to represent these things. You just imagine two balls attached to the string. A spring is there. Let two springs are there. One ball, to that ball, two balls are attached to two springs. H2O. You just remember water. Oxygen is there. Two hydrogens. Shape is V shape. So if oxygen and hydrogen, they will come closer and move away from each other. So that is your stretching vibration. Am I right? And in case of bending vibration, what happens? Let oxygen is on the plane, one hydrogen moving up the plane, one is moving down. Up and down motion of the hydrogen, keeping oxygen on the plane. So that is one type of bending. Okay, one is moving up, one is moving down, so that is like rocking. That is vibration is known as rocking vibration. Okay, so the bending vibrations are different types like scissoring, wagging, rocking, and twisting. Four types of bending vibrations are there, and stretching vibration is two types: symmetrical stretching, asymmetrical stretching. In case of water, if both hydrogen at a time come away from oxygen and come closer towards oxygen, same time, then it is symmetrical stretching. If one is coming away, one is moving towards oxygen, then it is asymmetrical stretching. So the stretching frequency generally it is nearly 3000 centimeter inverse, and in case of bending vibration, if it is in plane bending, then it is between 1300 to 1000. If it is out of plane bending, then between 700 to 1000 centimeter inverse. So depending upon this one, we can analyze the compound. Then NMR spectra, nuclear magnetic resonance. In this case, we use the radio wave. Okay, in the infrared, then higher frequency, higher wavelength or lower frequency is radio wave. So radio wave, what will happen? We have to make resonance with the nuclear spin of the atom, or the constituent atom of the compound. So how will you make the resonance? Little bit idea I am giving. If your nucleus contain even number of proton, because nucleus is having its own spin. Nucleus is moving. So when that spin is due to the proton and neutron which are present inside the nucleus. And these protons and neutrons, they have their own spin. Some may be clockwise, some may be anti-clockwise. So when the number of protons and neutrons sum total is even, then this spin is cancelled. Clockwise and anti-clockwise spin will be cancelled. But if there will be odd number of nucleons, that is proton and neutron, then there will be a resultant spin of the nucleus. So that spin, the basic principle or basic figure is not given here. So nucleus, it is having a spin like a top. You can see the top is having a precessional motion, and not to. So when it rotates, it spins around its own axis. Then also it is having some gyrational motion or precessional motion. That means the axis of rotation, it will just rotate around the axis of the gravitational field. Can you imagine? So that is known as the precessional motion or gyrational motion. So what will happen when you supply, if there will be a strong magnetic field, then this spin of the nucleus and the magnetic field, they will come alignment with each other. So there will be a flip of the nucleus from lower energy level to higher energy level in the presence of the external magnetic field. So what we have to do, we'll give a radio frequency there, so that which will counteract the magnetic field. So the external magnetic field and the radio wave, what we have given, so they will make a resonance. So what have been written here, so that's why the nuclear magnetic resonance. When the magnetic field is applied for recording NMR spectrum, the introduced magnetic field due to the ring current strengthen the applied field around the proton outside the ring, making them resonate at high delta value. Okay, so delta is the chemical shift. So what will happen, this is, you can see from the figure, this is the benzene nucleus. So benzene, this hydrogen which are just away, so benzene nucleus is having a pi electron system. So the electron, so in benzene the ring current affects the increase with the size of the ring and are higher from 6-member ring than 5-member ring. So first we'll go for benzene nucleus. So here what happens, this is the ring current, circulation of electrons in the ring current, and induced field is in this direction. So the ring current is in this direction, and here it is just in this direction. That means inside the ring, it is opposite of the applied magnetic field, and outside it is just parallel to the applied magnetic field. So that's why it will increase the resonance. But you can see here, in case of alkene, it is a pi electron cloud double bond. So when field is applied here, so the inside the internuclear axis, just it is opposite, and outside it is parallel to the axis. So the induced magnetic field reinforces the external magnetic field in the vicinity of protons. Hence, the protons are deshielded and appear downfield 4.5 to 6 ppm. In case of alkyne, triple bond is there, just opposite of alkene. You can see here, it is the molecule internuclear axis is perpendicular to the direction of applied field, but here the internuclear axis is parallel to the direction of field. So here the hydrogen or whatever alkyne group will there, this is the triple bond carbon, triple bond carbon. So here the induced magnetic field opposes the external magnetic field. Okay, Therefore, shielding of proton is occurred, and hence the peak will be upfilled at 2.5. Same proton, here hydrogen, here induced magnetic reinforces, means increases, so there will be deshielding. In this case also same, it reinforces, so there will be deshielding, but here it opposes. This is the proton. In this case, you see this is just opposite. This is along where hydrogen is there. The external field and the induced magnetic field, they are in the same direction. Here is the proton, same direction, proton, proton. But here is the hydrogen. So it is just opposite. Here same direction, but here it is opposite. So here there will be shielding. So it will be down, upfield. It will appear at upfield 2.5. Here they are at downfield. So that is the fundamental in nuclear magnetic resonance. So same thing in happen. The chemical shift value is related to the electron density of the ring carbon to which hydrogen is attached. So here you can see there is no hydrogen, but the carbon hydrogen is attached. So if a nitrogen atom is present in case of, as in case of pyridine, the alpha protons, they are deshielded. That means 2 and 6. These two protons, they are deshielded because this is due to the heteroatom. So that's why they will absorb at lower field. Deshielding, absorption at lower field. Shielding, absorption at higher field. The gamma protons, alpha, beta, gamma, this fourth one, also experience the deshielding. So 2, 6 and 4, these three protons, they are deshielded and they will absorb at lower field. Okay. But the gamma proton, that is experience the deshielding but lesser than alpha. But beta protons, they appear at slightly off field. So the value are given here. The H2, H6 protons, H2 and H6 at 8.52 ppm, and H4 at 7.75, and 35, H3 and H5 at 7.16, which is again slightly off field. But in case of benzene, you can see here all are at 7.24 because there is all protons are symmetrical here. So all protons, they will absorb in the NMR region at 7.24. All of you are there. I am not disconnected, na? Okay. Now these values are given for heterocyclic compounds. Okay, nitrogen has been, this value means for the proton which is attached to the carbon. So as already we have discussed this one, 8.52 for pyridine, the two alpha protons at 8.52, and this, which is at fourth position, that will be at 7.55, and 35 at 7.16. So other values are also given here. Two nitrogen atom, so this will be more off field. So 8.52 changes to 9.17. So 9.17 and these two are same symmetrical, so 7.52. Now in this case you can see this 9.17 is changes which is in between this one 9.26, again still off field because this is in between two heteroatoms, and this is just this one 7.8.78, 7.36. These values no need to remember, only we have to correlate because the nitrogen is a heteroatom. Due to more electronegativity, there will be more deshielding and it will be off field. Some 5-member compounds with heteroatom, the value are also given. So that you can remember. Then the aromaticity and reactivity. the aromaticity of 5-membered and 6-membered heterocyclic compounds. So you can see, you can judge by the vicinal coupling constant, JJ coupling constant. Vicinal coupling, that is otherwise known as the JJ coupling constant. So consider the following heterocyclic, this one. So let whatever heterocyclic ring is there here, and this is the benzene to which the heterocyclic ring is attached. So HA, SB and HC, three types of protons are there. This is also HC. So this is HC, this is the same. So this is SC. HA, SB and SC. So three types of protons are there. So one is ortho. Okay, this is meta. This is also meta. So if the ratio of ortho coupling constant, that is J ratio J AB and is to JBC, AB and BC. So if this constant will be 1 for the complete delocalization, and if this value is 0.5, then this is the reference value of localization. These constants are affected by ring angles and also the inductive effect. So the resonance energy per pi electron, the ratio is qualitatively correlated with the resonance energy per pi electron, REP value, to know about cyclic delocalization in aromatic system. There is a linear relationship. You can see the pyridine, the following resonance structure is occur. So basing upon that, we have some value. The resonance energy for thiophene, for pyrrole, and for furan. Then that also affects the bond length and finally the ring current. Here the REP value are given for benzene, for pyridine, pyrimidine, pyrazine, isoquinoline. So it is go on decreasing. For furan, it is minimum 0.007 because the 5-membered ring containing only the oxygen atom. So from NMR, we can find out the resonance energy and also that the ortho-pair ratio and the pi electron, what is the REP value, and the chemical behavior of reactivity. So aromatic compounds, they generally undergo substitution reaction, as we know, electrophilic substitution, and retain the aromatic ring. The reactivity of various compounds are different towards different agents, about which just we will study in the next chapter. Then there are some exercise. Okay, please do it. Answers also there. Any doubt? Otherwise, you move to the 3-membered heterocyclics, their synthesis, property, and characterization. All of you are there or not? Now on କରି କୁଆଡେ ପଳେଇଛ ସବୁ?
No, sir.
ବୁଝି ହଉଛି ନା ବୁଝି ହଉନି ନା ପରେ ପଢିକି ବୁଝିବ?
Good.
ବୁଝି ହଉଛି?
Sir.
ହଉ। ସେତିକି ଥିବ? सेकंड चैप्टर देखिबा
ଟିକେ ଦେଖିଦବା ସାର୍।
ଆଉ କେହି ନାହାନ୍ତି କି ତମେ ଲେଖା କହୁଛ ଆଉ କୁଆଡେ ଗଲେ ସବୁ?
ଅଛୁ ସାର୍ ଅଛୁ।
ହଁ ଏବେ ଜ୍ୟୋତି କହିବ ସେ ଦୀପକ
ଆଜ୍ଞା ସାର୍।
ଶିବ ତ ପ୍ରଥମରୁ ଅଛି ହଉ ହଉ ଓକେ ପୁରା ତ ହବନି ଗୋଟେ ଦେଖିବା ଗୋଟେ 3 member ring ଗୋଟେ ଷ୍ଟାର୍ଟ କରିବା ଆଉ azidine oxygen thyrene through synthesis and reaction of azidine. So this azidine, it can be synthesized by intramolecular cyclization reaction and cycloaddition reaction. So intramolecular cyclization reaction. So in this case, the 3-membered heterocyclics, they have high ring strain, as you know, because 3-membered, when 3 will be carbon. So as you know, all are single bonded carbon. So in that case, the carbon atom is sp3 hybridized. So bond angle is 109.5 degree of the tetrahedral angle. But in this case, if you consider this is planar structure, the bond angle is 60 degree. So this is very difficult. If you bond angle from 109, if you decrease to 60, then this bond or the compound will be highly under strain. So these are strain, you can say the strain compounds. So high ring strain as the chain length in the starting material is smaller because only 3-member, so chain length will be very small. So the two ends of the chain can provide appropriate conformation for cyclization. So first method by Gabriel method. Gabriel method, no, it is prepared from bromoaminoethane or beta bromomethylamine. Beta bromomethylamine when in presence of ethanolic potassium hydroxide. So what will happen? Generally, when ethanolic potassium hydroxide is there, if you any haloalkane, if haloalkane reacts with alcoholic potassium hydroxide, then there will be elimination reaction and it will be a double bond will be formed. Okay, here. So if it is bromoethane, you will get ethylene. But as the amino group is here, so by Gabriel method, it is phthalamide reaction. We know Gabriel's phthalamide reaction was also there, but it is not there. It is just like it's another method. So bromine will be removed, or it will react with ethanolic OH forming KBr, and if amine is not there, one hydrogen should be removed from here, like elimination reaction producing water. But removal of hydrogen from nitrogen is easy if one amine group is attached. So one hydrogen will be removed from nitrogen and bromine will be removed forming potassium bromide, and hydrogen will form water, so that nitrogen will be bonded to carbon forming azidine. So this reaction takes place via SN2 mechanism, and the halogen atom is displaced by amino group. Yes or no? This is not elimination, but this is substitution reaction. Bromine is substituted by nitrogen. But if amino group will not be there, that is quite an elimination reaction, but it is substitution reaction and follows bimolecular mechanism. So this reaction is SN2 mechanism, and the amino group is displaced, or halogen atom is displaced by amino group in intramolecular fashion. So this is intramolecular. First one, whatever there are two methods. First one is the intramolecular cyclization reaction. Similarly, substituted aziridines can be prepared in the similar way. One such sequence of reaction is illustrated starting with oxirane. So oxirane, if it reacts with primary amine, the simple reaction that you know, it will form oxo or hydroxyamine, substituted hydroxyamine, beta hydroxyamine. Then if you react with HCl, it will be chloro, hydroxyl will convert to chloro, and when we are giving base, this hydrogen and this chlorine will be removed, or this chlorine will be substituted by nitrogen. So we'll get this compound that is a substituted aziridine. So that means in case of aziridine, we have taken only amine, a primary amine. If you take a secondary amine, we will get substituted aziridine. As in this case, starting material is oxygen to prepare the substituted halo amine, means a secondary amine. The secondary amine will give the substituted aziridine. So oxidants reacts with ammonia or primary amine to give beta hydroxy amines, which can be further reacted with HCl to give chloroamine. Then that chloroamine undergo intramolecular cyclation to give substituted aziridine. Okay, then Wencker method. In this case, since the beta hydroxy amine or substituted amine, when reacts with sulfuric acid, the hydroxyl group will be converted to sulfate derivative by bisulfate, HSO3H. So bisulfate, when we react with a base, treated with a base, the substitute this that HO3S that and H that will be removed as sulfuric acid, and N or the OSO3H, the bisulfate group will be substituted by nitrogen, forming the substituted aziridine. If you take NH2 also, same thing will happen. You will get aziridine. If you are taking a secondary amine, then you will get substituted aziridine. This is also intramolecular cyclation of beta amino hydrogen sulfate derivative. Then in case of tetraalkyl aziridines, how to prepare tetraalkyl? So we have to take an alkene. Tetraalkylated alkene is used as the starting material. So when it reacts with nitrosyl chloride, we'll get a nitroso compound. Nitrous addition reaction, electrophilic addition of alkene, that you should know. So electrophile here NO plus and Cl minus. So you will get the nitroso chloride derivative. When reacts with reduced with stannous chloride and HCl, so that nitroso group will be converted to amine. It will be reduced to amine, NH2 beta haloamine. When treated with a base, will get aziridine, and the carbon atom is substituted by alkyl. So tetraalkyls substituted aziridine or tetraalkyl aziridine. So these are the method of preparation. Another method is there, that is Hassner's synthesis. Here also substituted aziridines can be synthesized. If you are taking the styrene here, so when iodocyanate is given here, INCO, and ether is the solvent. So iodocyanate. So when it reacts with styrene, so it gives one iodonium ion. So iodonium ion again reacts with the isocyanate, producing the trans-diaxial beta iodocyanate. When reacts with alcohol, ethanol, gives the beta iodocarbonate, and treated with alcoholic potassium hydroxide, it produces this intermediate which cyclizes to produce N-carboxyl aziridine, and upon saponification, that is first base hydrolysis, then removal of carboxylic acid or decarboxylation gives substituted aziridine. Similarly, beta amino alcohols, they'll also react, because when oxygen or ethylene oxide reacts with ammonia, gives one beta amino alcohol. When treated with bromine in presence of triphenyl phosphine, gives aziridine. From amino acid also we can prepare aziridine or substituted aziridine. By this method, we have taken valine, reacts with boron, producing beta amino alcohol. You know, when this reducing agent reduces to beta amino alcohol, again the same method when treated with bromine in presence of triphenyl phosphine gives substituted aziridine. Then the second method using cycloaddition reaction. Here the insertion reaction of nitrine to alkene yields aziridines. Azide in presence of sunlight produce nitrine and treated with alkene producing the aziridine substituted. So it is produced in low yield than other products are also formed when the nitrine is obtained photochemically or thermally from azide. So an alternative way to carry out the reaction at room temperature so that the alkene and azide yield a 1,2,3 triazole intermediate by 1,3 dipolar addition as shown below. This one substituted aziridine. So rest the reactions and others we'll see in the next class tomorrow. Okay.
Thank you, sir.
Okay. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.